Hey everyone, Morgan here. So we're looking at the AP outline called Liquids and Solids. Okay, and we're going to go through this unit as a slide deck. I typically don't like to do slide decks, but it does work very well for this material because I don't have access to all the models that I'd be using to cover it. So let's start off by talking about the difference between a solid, a liquid, and a gas. Chemically, there isn't a difference. Okay. The only real distance in here is the difference in here is the distance between the atoms. Okay. The solids, they've got particles that are close together. They're still moving. They're kind of locked in place, but they can vibrate where they are. Liquids have particles that are close together, but they're much more mobile. And gases have particles that are moving very chaotically and randomly. Now, solids themselves would take on some type of an arrangement that looks like this, okay, a very regular and repeating pattern. They're going to be close together, whatever those particles might be. They're fixed in space, but they can be vibrating. Now, the two most important points are that they have a fixed volume and a fixed shape. Now, for liquids, the particles are still very close together to each other, but IMFs are still interacting between them. They have a lot more freedom in their motion, which directions they can move around in. They'll still have a fixed volume, however, and that's a very important point, but they will take the shape of the container, so they don't have a fixed shape. So again, two really important points here: fixed volume, and they take the shape of the container. Now let's understand that this does not mean that the molecules involved are changing their molecular geometry. They're not. This is the shape of the overall volume of the liquid, not of individual molecules. Now, for gases, the particles fly around really far apart from each other, big distances between them. We used to call that the mean free path. The motion is random and chaotic. We can't predict what it's going to be. Gases do not have a fixed volume. Big important point. And gases will also take the shape of their container. Now, it is worth pointing out to you that in this unit, the particulate diagrams are very important. So these three diagrams that I've just shown you, you should have in your notes, and you should be able to reproduce them to describe the behavior of a solid, a liquid, or a gas. I'm very fond of this particular diagram because it shows very nicely. It's the tail, actually three tails per particle. So you see that the particles are flying around. Okay, so what happens when a substance melts? Well, chemical change does not happen. The substance is still the same substance. Okay, the particles will be moving faster. They can spread out a bit. Okay, the motion is a little more random. They have more kinetic energy. But when you melt an ice cube, the water that was in the ice cube is the same water that's in the liquid water. It's water. Now, common mistake. So a lot of people think the volume gets bigger. And for some substances, it can. It doesn't for water. But for some substances, the volume can increase. But that doesn't mean that the particles are getting bigger. It just means that the spaces between them are getting bigger. So what happens when a substance boils? Well, it's pretty just much more of the same. Much larger distances between the particles, lots more kinetic energy. Okay, sorry. And very random, chaotic behavior of the particles. But the particles are still the same particles. Emphasizing here, no chemical change. So what does not happen? New stuff is not made. There is no chemical change. Okay, now, we examined this reaction back in the unit on thermochemistry, and we talked about heats that were called latent heats or hidden heats, heats associated with phase changes. This is the heat of fusion for water. If we want to melt a mole of water, we have to put in basically 6 kilojoules. If we want to boil a mole of water, we have to put in practically 10 times as much. So what is this huge difference? Why is this happening? Okay. Why is it so much more challenging to boil water than to melt it? That has to do with us overcoming intermolecular forces. Okay? What's going on here is hydrogen bonding. And the hydrogen bonding is keeping the water molecules close together, side by side. And to boil them, we have to overcome those intermolecular forces, which in the case of hydrogen bonding is quite strong. So, our theme for a good chunk of this chapter is going to be melting points and boiling points, because they are a good description of a compound or any substance. It doesn't have to be a compound. So what determines the melting and boiling points? Well, we're going to call it interparticle forces. I should avoid using the phrase intermolecular forces because some of the things that we're going to talk about aren't molecules, or in some cases we're just going to have ions. Okay, in some cases plain old atoms. So we'll call them interparticle forces. Now, the whole idea behind this is what's going to hold these particles side by side next to each other. And when something melts or boils, we have to overcome those forces. So we should distinguish then between inter and intramolecular forces. This is basically us distinguishing between bonds and attractive forces. So this is an intermolecular force, hydrogen bonding specifically. It goes between the first water molecule and the other water molecule. Now, I chose this diagram specifically because it is part of a former AP exam multiple choice question. Okay? This would be an intramolecular force, an actual bond that's inside of one water molecule. To have IMFs, you have to have two molecules. They can be two molecules of the same substance, or they can be different ones, but you have to have two molecules. So, there are three intermolecular forces the way most books describe them: London dispersion forces, dipole-dipole forces, and hydrogen bonding. However, a new term is becoming more and more popular called the ion dipole force. Some books put it as a separate one in the list, but really it's a subset of dipole-dipole forces, so I wouldn't worry about the nomenclature bit here all that much. Just as long as you're describing the two particles involved, you're fine. Now, common mistake that's made right here. Many people and textbooks would say that this is also the order of their strength, and that is not 100% true. There are London dispersion forces that are stronger than dipole-dipole forces. Let's just accept that. Okay? And we'll see some examples of that as we go. So, if you read your AP biology book thoroughly, you probably came across the phrase van der Waals forces. Now, this is an antiquated name that chemists don't use anymore. It included both LDFs and dipole-dipoles, and the name came about before we knew what electrons were. So we were not able to actually describe the forces accurately. Now, van der Waals, if you remember, you see here on this stamp van der Waals equation, okay? Van der Waals talked about the attractive forces between particles in a gas, which were predominantly LDFs and dipole-dipoles, although occasionally hydrogen bonding. Okay? So, hydrogen bonding is separate. Hydrogen bonding is not part of van der Waals forces. It's strong enough that we've actually known about it for a long time. So it's been its own category. So let's look at what we call LDFs, London dispersion forces, first. They are temporarily induced dipole moments. Now, that's a good diagram for you to take a look at. I would pause the video and reproduce this one inside of your notes. But what I need you to kind of picture is this old party trick where you take a balloon and you blow it up. You rub it on your hair and then stick it to the wall. What you have done is you have temporarily induced a charge on that balloon. Okay, I can't do that anymore because, well, you actually need hair to be able to do this. Okay, so I'm at a disadvantage. So, what happens is a charge of some type on an atom or on a molecule, okay, will cause a separation of charge. Okay, now, since atom A has a positive side and a negative side, atom B will get the same, because the positive side on atom A attracts the negative on atom B. Now, and the same thing would happen with a molecule. But understand something. Electrons don't stop moving. These are very short. They form, they leave. They form, they leave. Okay? But they happen often. So it's happening so quickly that it's almost as if these are there all the time. They're just changing where they are. So they're temporarily induced dipoles. Now, my favorite example of this has got to be the halogen family. We'll talk about Cl2, Br2, and I2. The bonding's identical. You've got homonuclear diatomic molecules. They're linear. They're perfectly covalent bonds. It's kind of dull, all right, just to think about the bonding involved. But the impact of the intermolecular forces is very pronounced. So this is chlorine, and at room temperature, chlorine is a gas. This is bromine, and at room temperature, bromine is a liquid. This is iodine, and iodine at room temperature is a solid. So what's going on here? As you increase the number of electrons present, going from chlorine to bromine to iodine, you increase the polarizability of the electron cloud around the molecule. And if it's more polarizable, that means you have a stronger IMF. Okay? So that can keep, in the case of iodine, the molecules close enough together that they form a solid. However, it's not that strong an IMF. If I were to put a crystal of iodine in my hand and let it warm up, it would sublime, which you kind of see in this picture. Now, bromine has a very high vapor pressure also. So I don't actually have a open bottle of bromine in my classroom. I have a little sealed one that I can show. But if we were to let it sit around, you would get that kind of reddish brown cloud of the vapor coming off of the liquid. So the magic phrase really for all of this when you're writing your essays is a more polarizable electron cloud. The more polarizable is, the stronger the attractive force, What makes it more polarizable? More electrons being present. Okay, now dipole-dipole forces. Everything we've just said, same thing, except that the dipole moments are permanent, okay, rather than being temporary. So you have to have molecules that have dipole moments, okay, something like HCl. It's a really good diagram here, okay, showing you what it might look like. So pause if necessary, do a drawing, get out some crayons or something so you can match up the colors. So what you see here is the positive sides attracting the negative sides. Now, here's what's misleading. HCl is a gas at room temperature. You're always working with an aqueous solution of it, but actual HCl is a gas at room temperature. Cl2 is a gas at room temperature. Chlorine has a higher boiling point than HCl does, even though chlorine's only got London dispersion forces. It's just that the LDFs in Cl2 are stronger than the dipole-dipole forces in HCl. Why? More electrons. It's a more polarizable electron cloud. Now, if something has a dipole moment, that's a polarized electron cloud. Okay. And now on to something that just makes my life miserable. Having to tell people that hydrogen bonding is not actually a bond. Worst name in all of chemistry. Hydrogen bonding is an attractive force. It is an attraction between a hydrogen atom, and then you'd need one of nitrogen, oxygen, or fluorine. And it only works with those elements. Why? Because they're small. Now, this is all Coulomb's law stuff. Size of the charge, distance between them. So since they're all small, they can be close together. Now, the charge itself would be their electronegativity. Chlorine, which is not on this list, has the same electronegativity as nitrogen. But it can't form hydrogen bonding because it's too big. And the atoms can't get close enough to each other for this to happen. Now, when I was in school, I had a professor tell me that hydrogen bonding was an especially strong dipole-dipole force. That's not a lie. It's just not useful. It doesn't actually tell me what's going on here. Okay? It's a bit of a description, but that's it. It's not an explanation. So everything here is based on Coulomb's law. And since hydrogen is small, it can get up close and personal with the nitrogen, oxygens, and fluorines and form hydrogen bonding. And yeah, it is a dipole-dipole force. And it is really strong. I mean, like 10% the strength of a covalent bond. But you have to know what elements are involved. Now, this graph is one of my all-time favorites. It really explains how strong an effect hydrogen bonding is. We're going to look at the lowest of these lines, which is in blue here. And these are the boiling points of the hydrides of elements from a certain group. Now for group 4, CH4, SiH4, GeH4, grab your periodic table, take a look at it. You'll see what I'm talking about. These are all vertical groups on the periodic table. And that's pretty much the way the trend should be. And the only difference really between these would be the number of electrons or how polarizable the electron cloud is. And as you get more electrons, you end up getting higher boiling points. Now the green line, that's for group 5 or 15, depending on which table you're looking at. Ammonia is not following the pattern. In fact, there are some outliers on here. Water, HF, and ammonia, which are your 3 best molecules ever to use to describe hydrogen bonding. Okay, those molecules have hydrogen bonding. And the IMF there is so incredibly strong that their boiling points go completely out of whack. Water is an example. If hydrogen bonding didn't exist, water's boiling point would be somewhere around negative 70 degrees Celsius rather than 100 degrees Celsius. There'd be no liquid water on this planet. So without hydrogen bonding, we wouldn't be here. Okay. Now, it isn't just the presence of the nitrogen, oxygen, or fluorine that matters. The hydrogen atom has to be directly bonded to it. So within that one molecule, water, the oxygens and the hydrogens are bonded to each other. And that means that you can have hydrogen bonding with a second water molecule. So we got to look at some structural stuff today. Water, boiling point's about 100 degrees, okay, Celsius. Now this is what the hydrogen bonding would look like in liquid water, and this is what it would look like in solid water. And you'll notice there are a lot of attractions for every water molecule. So I am going to tell you to pause and spend some time drawing a nice picture here. Some people might cheat. You can probably print one out from the net and paste it into your lecture outline, but better to draw it, okay, so that you actually know what's going on. Okay, you've tuned back in at this point. Let's go on and let's compare this to some other molecules, like HF. Now, HF is basically a linear polymer type structure. An H covalently bonded to an F, and then a hydrogen bonding attraction to the next hydrogen, which is covalently bonded to an F, and then a hydrogen bonding attraction, etc., etc. So the red arrows in this diagram, that shows you the length of this hydrogen bond, which is the dotted line. And then you'll notice that the solid line, which is the covalent bond, is much, much shorter. Okay? Now, it's a weaker attraction this time than it was in water, because each HF is really only experiencing a hydrogen bond on the left side and on the right side. It's not three-dimensional. So it turns out the boiling point of HF is really about 20, it's like 19.5 degrees Celsius. That is 1/5 of what it is for water. That's low. Okay? Why is this? Well, it's just because it does have hydrogen bonding, just not as much as the water molecules. Again, pause right here, draw your pictures, tune back in. Okay. Ethanol C2H5OH. This is the structure. Now, you see that the OH group on the end makes it possible to have hydrogen bonding because the H is bonded directly to the O. I'm not really worried about the H's bonded to the carbons. They're not taking part in this. So ethanol can be attracted to water. That's why it's very, very water soluble. Okay. Or it can be attracted to other ethanols. And if it's just pure ethanol, no water involved, the boiling point's about 78.4 degrees Celsius. Really quite high because of those OH groups at the end. And a bit of LDF. There's some London dispersion forces going on because of the electron cloud also. So pause, draw this picture. Okay, now we're going to look at a structural isomer of ethanol, dimethyl ether. Exact same atoms, just put together in a different way. Now the big difference to notice here is that the oxygens are bonded to carbons. There is no hydrogen directly bonded to the oxygen. There is no possibility of hydrogen bonding. So because of that, you're going to end up with a much lower boiling point. Okay? Let's see. I can get rid of that little window there for you. Okay, now we'll add another carbon in and make propanone. Again, no hydrogen bonded directly to the oxygen. The boiling point's about 56 degrees. Now that's about 20 degrees higher than the one we just looked at. This is because we have an increase in London dispersion forces. Because of one more carbon being present, we have a more polarizable electron cloud. No hydrogen bonding. It's got a permanent dipole moment, just like the last one did, but it doesn't have any hydrogen bonding. Ethanal, slightly different structure. Make sure you get it drawn in. Pause if you have to. Got a dipole moment, but it does not have hydrogen bonding because that oxygen is not directly bonded to a hydrogen atom. Therefore, the boiling point is pretty low. It's down about 20 degrees Celsius, 20.2 degrees Celsius. So I think that illustrates for you really quite nicely how strong an effect hydrogen bonding has on boiling points. Now for the last one, we're going to look at 3 isomers of pentane. They all have the exact same molecular formula, but they have different structures. Okay? Now what you'll notice looking here is that the surface area decreases as we go from left to right. Decreasing surface area. Now, that's going to have an effect on how much of the LDF can be felt. For the first one, we have a boiling point of 36.2 degrees Celsius, then 27.9, and finally 9.5 all degrees Celsius. So what I want you to picture are 2 pieces of Velcro, bring them together, nice straight Velcro strip, and try to pull them straight apart. It's challenging when you're pulling straight out. Now, this time, wrap that Velcro around a tennis ball. And do the same on the second piece of Velcro on another tennis ball. So that when you bring those 2 together, the only place where the Velcro touches the other Velcro is a much smaller surface area, about maybe 1 inch long. So it's easier to pull that apart now than when the entire Velcro strip was attached. That's what's going on here. When you have that structure on the far right, okay, the molecules don't get as close together to each other. All right, so that's the end of this lecture, and you can tune back in into the next one when we start talking about liquids. All right, this is Morgan, signing off.